Welcome, everybody. We're working on Unit 6 tonight, which is the part 2 of learning about supervised learning for machine learning. Our agenda tonight is what you see up on the screen here. We're going to talk about the concept of probability and what that means and why it's important for machine learning, how machine learning uses classification with a probability. We will learn what a decision tree is and how to create one with Python code and without. And we'll also look at how supervised learning can be applied to real world scenarios. And we'll talk about a bunch of different concepts as we move through here. And some of them are pretty math related, fortunately, or unfortunately, depending on how you look at it. All right. So we did talk about supervised learning last week, and we're going to continue that this week. And our attention now turns to this concept of probability. And basically, probability is, as it states there, the likelihood an event occurring. We're going to see examples with decks of cards here, or rolling a dice, or is it going to rain today, or is it not going to rain today? And it says here we deal with probability in almost all aspects of our lives every day. All right. And look at some of these questions because I think they're all kind of to get you into this mindset. What is the likelihood that if you flip a coin, that it's a head or a tail? Or the super unlikely scenario that it stands on edge, right? Highly unlikely, highly unlikely. What's the likelihood that you flip a coin 3 times and they are all heads? It's a different probability, right? Or will it rain tomorrow? Or what's the chances that James will bring his lunch to school tomorrow? Or how likely is your best friend to pass the quiz? That type of thing. And you think about that, what kind of answer do you give to those things? Well, the answer is typically a percentage, right? Percentage probability, right? So keep that in the back of your head. The formula for probability is pretty straight ahead. So the number of that event actually happening. So if I flip a coin, did it become a head or not? If it did, well, it happened. How many times did I flip the coin? Right. And then you take that and you divide it and you get the probability in the form of a percentage. So basically, probability, really, if you want to analyze, it's just a ratio, right? It's just a ratio. And how many times did the thing you want to occur happen out of all the times that it could have happened, right? Every time there's a thunderstorm, how likely is it that a lightning bolt is going to strike you? What's the probability of that? Thankfully, it's very slim, right? All right. So we're going to start talking about some of the scenarios here. So we're going to go through this imaginary scenario. So let's maybe even do the math on it and say, what's the probability of flipping a coin and getting a head? Well, that's pretty easy, right? It's one side or the other. So what's the probability? There's 2 possibilities. So half the time it's going to be a head. Simple, right? Every time you flip a coin as a discrete event, 50% of the time it's tails, 50% heads, right? All right. Now, if you guys want, if you actually have, nobody carries coins anymore, right? So flip a coin. I got to go find one, right? That was never the case in the old days. We always had coins in our pocket. All right. So you flip it once. Okay, that's the probability. It's 50-50. But now if I flip it 3 times, what's the probability of getting heads all 3 times? Interesting, right? Now 10 times or now 20 times. And do you guys know how astronomically impossible it is to flip a coin and get heads like 20 times in a row? Yeah. And Paul's like throwing math in there for, yeah, it multiplies. And in fact, if you guys want, let's just like jump out to an AI here. Let's just ask. All right, we'll do Chat GPT since I was using it earlier today. What's the probability of flipping a coin and getting heads 20 times in a row? Let's see if read my voice first. So that I don't usually do this with ChatGPT. And I'm going to say it's pretty darn slow in responding. Now I feel like I should have typed it. Okay. Yeah, that's correct. So the voice recognition is a little slow there, but it was accurate. And there's your math. So it's one chance in 1 million that you would get 20 heads in a row. Like, yeah, but that's pretty crazy, right? And they show you the formula for it and everything like that. But that's how astronomically impossible that is. It's a very, very difficult task, right? And not impossible, but highly unlikely, right? Um, yeah, and so I think we answered all these questions here. So why is this important for machine learning? Because probability is a predictor, right? The prediction is when I flip a coin, it's either going to be heads or tails. So 50% chance of tails, 50% chance of heads. And it says it predicts the future using past data. So a coin flip is pretty determinate. But if I play, let's say, a different type of game, let's say I play darts, what is the likelihood of me throwing a dart and getting a bullseye? If it examines all my previous throws, let's say I have 500 throws at the dartboard, and out of those 500 throws, I hit the bullseye twice. Well, the probability is pretty small, right? It's a very small percentage, right? And this is important, right? Because we can look at past events to help predict what the future events might hold. So chances are very slim that I'll hit the bullseye, is kind of the point. So, but if I have a tendency when I throw the darts to always throw them low and hit like 16 or something like that, or 19, right, on a dartboard, those percentages are probably higher, and they can predict that based upon what happened before. So I am going to play this little video here. It's about 7 minutes long, but I'm going to speed it up slightly, just so it goes a little shorter. This comes from I forget which university it is, but this is a university lecturer talking about uncertainty and predictions. And think about the key points of this video as I play it. I'm going to leave it in small screen mode like this. Closed captioning is on, and playback speed is going up slightly.
We're going to spend a fair amount of time talking about probability, and it's worth asking, why is probability so important to machine learning? I want to start with this quote from David Hume, that even after the observation of the frequent or constant conjunction of objects, we have no reason to draw any inference concerning any object beyond those of which we have had experience. What he's talking about here is the task of induction. And in particular, he's talking about whether or not we can make predictions about what will happen tomorrow given what's happened so far. That is the past predictive of the future? This is important to us in machine learning because the idea of generalization is that the past is predictive of the future. That is, we really believe that we can look at a bunch of training data and make interesting and useful predictions about data we have never seen before. So why is generalization possible? Well, it's possible because we're willing to commit ourselves to structure in the data that we expect to see again and again. That is to say, that in order to generalize, we must make assumptions about the structure of the world. There are many different ways to specify these kinds of assumptions, but one of the most powerful frameworks is the calculus of probabilities. Here's a video from NVIDIA on the task of scene segmentation. This is a critical task for self-driving cars as it's necessary to understand the car's surroundings. Here pixels are being labeled according to whether or not they're a car or the ground or a person. And of course the idea is for the car to use this information to get to its destination safely. It's helpful to think about all the different ways that noise and uncertainty can come into play in a problem like this. For example, the sensor readings that the car is receiving might be noisy. This could be due to the sensor itself, or a bumpy road, or weather conditions, or any number of factors. Additionally, the environment itself might have unpredictable dynamics. It might be hard to anticipate exactly what a car or a pedestrian is going to do. Plus, there might be a lot of random things that could happen, like you could blow a tire or a stop sign could get knocked over. Then there might be uncertainty in what the optimal parameters should be due to limited training data. The car should probably stop if an elephant suddenly runs out into the road, but how many times have you seen that in your training data? And of course, on top of that, it's not like your model is a perfect representation of the real dynamics of the world. In the self-driving car example, it's not like you can build a complete theory of mind of all of the other drivers on the road. Then, even if you could write down some amazing model for the entire world and had an unlimited amount of data, on the car you still have a limited amount of computation in order to make predictions. Finally, even if you have tons of data and have built a fantastic model, the environment itself might change and you need to adapt. It turns out that it's very helpful to reason about a lot of these processes in terms of random variables and probability. Even in relatively straightforward classification settings, we still like to talk about probabilities. For example, imagine building a simple image classifier for animals. It's helpful both at training time and at testing time to be able to represent its predictions in terms of probabilities. Rather than saying definitely a cat or definitely a dog, instead, these kinds of classifiers put probability distributions over the different possible labels. Ideally then, when encountering a legitimately ambiguous piece of data, the classifier can represent its uncertainty. Regression provides another way to think about this. Imagine that we're trying to model some true function represented by this dashed line. We've observed 3 data represented by the black circles. Given that we only have 3 observations, there are many different functions that could explain these data. Rather than commit ourselves to only one function, it's helpful to try to represent all the possible functions that are supported by the evidence. Then, when we make predictions, we account for all of these possible explanations of the world. It turns out, too, that this provides us with a really nice way to update old information with new observations. And ideally, we'd be able to boil all of these hypotheses off into distributions over things we might see at new locations. Here I'm illustrating this as isocontours of a predictive distribution conditioned on the 3 observed points. That's just a few of the ways that probability informs supervised learning, but there's plenty more. For example, a large amount of machine learning is really maximum likelihood estimation of a conditional probability. On the more theoretical side, a lot of the guarantees that we achieve in machine learning arise from the framework of empirical risk minimization. As yet another example, you've been hearing a lot about deep learning. Well, deep learning depends significantly on stochastic optimization for it to work. Finally, a lot of the most famous theoretical results are based on the idea of PAC bounds, where PAC stands for probably approximately correct. Most of those examples are about supervised learning. In unsupervised learning, probabilistic modeling is even more important. In fact, many unsupervised learning algorithms really boil down to density estimation. If you've heard about people talking about generative modeling or things called generative adversarial networks, well, what they were talking about was modeling a probability distribution from data and then sampling from it to get new kinds of data. Those faces on the left aren't faces of anyone real. They are samples from a probability distribution that was learned from data. On the right is an illustration of a similar kind of idea applied to small molecules. The idea is to be able to train a model on a large data set of, say, successful drugs, and then sample from that model to invent new kinds of molecules. This particular figure is taken from the recent work of one of my students, Ari Sef, who is also a TA of this course. Random variables also provide a powerful framework for thinking about latent structure in data. There are many, many examples of this kind of modeling, but here are 3 just from my own work with applications in neuroscience, astronomy, and sports analytics. In neuroscience, we use latent variable models to capture behavior and then connect that to neural activity. In astronomy, we use latent variable models to capture the properties of remote light sources like galaxies, for which we only have weak and noisy observations. And in sports analytics, latent variables give us a way to think about the characteristics of different players. Here, in work by my former student Andy Miller, you can see how the shooting patterns of NBA players can be broken down into latent factors. Player skill estimation in online video games provides another fun example of probabilistic latent variable modeling. You'd like to estimate player skill in order to match people up so that they have a good time. However, the outcomes of the games are noisy, and in multiplayer games, you only get weak information about the individual skill levels. Probabilistic models are used to estimate skill for games played by millions of people every day. Another important area of machine learning is sequential decision-making. We can understand a lot of different AI-type tasks as sequential decision-making under uncertainty. When playing a game, for example, you don't know what your opponent's move is going to be. When you're navigating, you may not know exactly where you are. And when you're making financial trades, you don't know how the market is going to move. In robotics, you may not have a perfect model of the kind of objects that you're trying to manipulate. In all of these cases, we not only use probabilities to describe noise in the world and stochastic dynamics, but we also use random variables to describe our own uncertainty about the state of things. So even though it may not be obvious at first, probability is totally fundamental to machine learning. You're going to want to take the time to understand as much probability as you can.
All right, some pretty heavy stuff, right? I mean, in terms of how it's presented, and I think he did a really nice job about talking about why it's important, throwing some pretty deep concepts at you at the same time from like a university level type of approach, right? They're throwing words at you like stochastic, like what the heck does that mean? Right? And you should be Googling it if you're not sure, but it basically talks about, it's about randomness is really what stochastic is related to. So if you were to summarize the key points of the video, I'm not sure if you would be able to do it off the top of your head without watching it again, but it is really important relative to the application to machine learning and how it operates. And hopefully at least some of his examples or some of the things that were going on maybe trigger a couple of things in your head as you're thinking about this stuff. All right. All right, let's see how they use this now for doing classification. for machine learning. And before you do this, you have to understand that we're often dealing with things that are random. So we have variables in our equations that are not known, right? That we're trying to predict, basically. And there's three different types of probability. Understanding what these probabilities are is important, because if you picked up from that little video segment, machine learning uses the third one predominantly to do some of its pattern recognition and classification, really focusing on the conditional probability of something. All right. So once again, let's review this. It says probability is the predicted outcome of a random variable. So for example, I pick up a dice and I throw it. What is the probability of getting whatever, right? It's easy to find the possibility for a single random variable like a dice, right? Because it's simple, right? There's six sides. So there's one chance in six that will land on any one of those sides, right? Um, if you have more than one random variable interacting with each other, well, that changes things a lot. So, for example, it's one thing if I'm throwing one dice, but what if I'm throwing two? Or let's complicate it even more. Let's play Yahtzee and throw five dice at a time, right? What are the possibilities there, right? That's kind of interesting. And when you think back to our probability equations, like, the game Yahtzee, for example, you scream out Yahtzee when you get five of the same number, right? That's like a thing, right? If you've never played it, good for you, right? As a kid, we didn't have internet, so I played that game, so in machine learning, unfortunately, we do have to deal with multiple random variables all the time. And then we have to figure out how to, which one of those three techniques we're going to use. All right. So as an overview, a joint probability is the probability of event A and event B happening together, right? So I have this thing, and what's the probability that they're both going to happen together, right? Then we have what we call marginal probability, is what's the probability of event A happening regardless of what B does. Okay. So we're just looking at one. So it's marginal probability. Conditional probability is kind of the inverse of number two, if you think about it that way. It's like, what's the probability of A happening given that B has happened? So if B happens, what's the probability A is going to happen? Like, how is that affecting it? Right. So it has an effect on it. So let's just kind of review all of these really quick. And they start to go into the card game scenarios here. So if you guys, assuming that everybody knows what a deck of cards is, a deck of cards has 52 cards going from ace through 10, king, queen, jack, right? And there's four suits. There's spades, clubs, diamonds, and hearts. Diamonds and hearts are red, spades and clubs are black, right? And I make this assumption that most people know this, and there's 13 cards per suit, which is kind of a weird number, right? So it makes for really weird probabilities and stuff. And so you should always be impressed when people are really good at playing card games and can count cards and remember all that stuff, that they're not doing it with they're doing it with kind of basically with a base 13 number system in a way. All right. So let's look at this joint probability. So let's assume we have a deck of cards, and event A is picking the number 6 out of the deck of cards. Well, how many number 6s are there? Well, there are 4, right? So this is A here, the circle on the left. There's 4 chances out of 52 to get a 6. Event B is that we get all the red cards. Well, there's 2 of those are 6s, right? And then there's otherwise 26 red cards, right? And they're all shown on the screen here. Joint probability is both getting 6s and red cards. So joint probability would really be highlighted by the stuff here in the middle. That's the joint probability. So it's the intersection where the 6 cards and the 6 of heart and 6 of diamond reside. And that's what we're seeing on the screen here. make my line a little bigger, and I'm going to change my color, by the way. There we go. A little better. Okay. Moving on to the next slide. All right. So if you want to do this mathematically, right, and I'm not, just be thankful that I'm not making you do math exercises like this in this class to show me your proofs and all that kind of stuff. This is what statistics classes are for. But if you've had a statistics class, some of the nomenclature or the syntax of the math equations should look kind of familiar, I'm hoping. And you'll notice that it says event A is picking the number 6. Event B is all the red cards. We already determined that there's 4 number 6s, so that's 4 out of 52, right? And 26 red cards, so 26 out of 52. And notice how this is listed. P stands for probability. And then what is the event that we're looking for? That A equals 6 or B equals red, right? And then you can type the numbers in, and if you follow through the equation here and multiply through the numbers, there's 1 chance in 26 of getting the 2 red 6s. And think about it. That's 2 cards out of 52, right? Which as a fraction, so if I was to write that on 2 out of 52, if you were to reduce that fraction, it would be 1 out of 26. So that's the probability. And yes, you can convert that to a percentage, but it's 1 chance in 26, basically. These symbols here, by the way, this symbol here stands for intersection, and an upright U stands for union. And if you recall on the previous slide, this joint probability is an intersection. That's why it's listed. The intersection of 6s and red cards is the point here. Then there's marginal probability. And once again, let's look at the same scenario, picking the 6s and all the red cards, right? Those are the 2 events. Marginal probability is the probability of a specific event regardless of the other event, right? So we're not looking at both, we're just looking at one, right? So if we look at the same scenario, right? Same numbers up here, but we're not concerned with, right, A in this. We're only concerned about getting red cards. So if we're only concerned about red cards, we basically summarily ignore the A scenario, and it's a 50-50 chance of getting a red card. That makes sense. 26 chances out of 52, that reduces down to 50%. All right. Now we have the conditional probability, right? Same scenario. And that's defined as the probability of event A given that B has happened. So B has already happened. We already have all the red cards in our hand. So what's the probability that we're going to get 4 6s now that B has already happened? That's the approach. And notice how this is written, right? The conditional probability is expressed as the probability of A happening given that B has already happened. And the breakdown are 2 probability equations. One is the intersection versus divided by basically the probability of B happening in itself. Now, if you think about that, the intersection of A and B is what? The 2 red 6s, right? And this is all the red cards. Okay, so if we fast forward to the math part of it, that's a 1 in 26 chance over a 1 in 2 chance, which reduces down to 1 of 13. Yeah, if you do the math on that, that's how it works out. So 1 chance in 13 that you'll get 2 red 6s. That's the conditional probability. All right. So they have this as an exercise. And as I said before, if we had more ample class time, I would like have you calculate this stuff, because there is value in doing that just to see how it works. But if you were to calculate, for example, the joint probability of getting odds from the dice and the head, of a coin, or the marginal probability of getting 3 or less from the dice, the conditional probability of getting events from the dice given the tail from the coin. So what they're doing is they're combining a dice roll with a coin toss. How do the two affect each other? Do they? Yeah, this is where um, we sit. And you know what? And we do this assumption thing too. Um, all right, let's kind of skip over that right now. But in a normal world, I would take the time to plow through the math on that. We do need to know what a probability distribution is, and these are often represented graphically in many formats, right? So that we can see what it looks like and where the probabilities fall. So what it is by definition, as it says here, is it shows all the possible value of the random variable and how often they happen. So if I was to, for example, roll a dice, all 6 sides of the dice have an equal amount of probability. So how often should each one of those sides happen? Well, the answer would be 1 in 6 times, right? And if I flip a coin, how often should it be heads or how often should it be tails? That's pretty predictable because the choices are finite. They're kind of not binary, but they're controlled, is the point. There's a bunch of different types of probability distributions, and some of these you do learn about when you take your statistics class. We're going to look at some of these and how they lay out and what they mean. And then I will also take a look at the normal distribution, and then we can talk about the other ones. I'll show you what the process is here from the authors of this PowerPoint. So let's look at the probability distributions, and we'll start with the Bernoulli distribution, which basically has 2 possible outcomes. So this applies really well to the coin scenario, and it only applies to a single coin toss, right? So there's only 2 outcomes: tails or heads or tails, right? One or nothing, and usually when we do this mathematically, 1 is success and 0 is failure, right? True, false kind of thing. If you look at the proof for it, right? You look at the probability of each one happening, whether it's going to happen or not. And the not is expressed as 1 minus p. So in other words, 0. And that's super worried about like the functional aspect of the math here. But we just want to kind of look at it and then see how it applies to real world scenarios, like what they say here. So if we wanted to look at the expected value of a random variable, there is a formula for it that you can put in with this distribution, and then the variance of that random variable, like how much it might change. Now, given the scenario that it's one or the other, there's not a lot of variance, right? Because you have 2 states. Here's examples, right? It says, will it rain tomorrow? Well, it's either yes or no. Now, there's a percentage chance that it will rain, but it either does or it doesn't. Sometimes they predict rain and we don't get anything. Sometimes they don't predict rain and we get it. So I mean, they can be wrong. And then this must be the carry on from the football thing. Will Real Madrid win the match tonight? In a sports, outcomes are like that too. You have a winner and a loser, right? Well, every once in a while, there's a tie, right? So there's a third possibility in sports, in some sports. All right. If I were to take a look at the uniform distribution, in this case, all the outcomes are equal or equally likely. And an example we use for this is a 6-sided dice or die, right? It's got the numbers 1 through 6 on it. Each side is equally likely to appear. And this can also apply to a coin toss, though. This is kind of interesting because that's only got 2 states that seems to fit with the Bernoulli thing, but a uniform distribution nonetheless. It's either heads or tails, right? A dice, one of the sides 1 through 6. And there, if you were to plot that on a graph, all the possibilities will fall into this chart. All of them are equally possible. right? Depending on how many possibilities there are. And that, if it falls outside that range, it's basically uh, kind of irrelevant, actually. Um, Once again, we look at the expected value of a random variable, and there's a formula for that, and the variance of a random variable, and there's a formula for that. Now, be mindful of the fact, right? The tools that we will use to kind of analyze this stuff do this math in the background by virtue of the Python library that we're using. You just need to know which tool to apply, right? You're not going to be manually crunching the numbers. Here's some applications of this. Guessing somebody's birthday, like which day of the year. Well, that's one chance out of 365. It's equally likely that the person was born on one of those days, except for that February 29th day that happens once in a while, right? But you get that. Okay. I'm just trying to throw a little wrench in the works. Rolling a dice is a good one, or getting a specific card from a deck of cards, right? Equal chance of 52 possibilities. But all of those fall into uniform distributions because no single day is more likely than another to happen. No side of the dice is more likely to come up, and no card from the deck is more likely to come up. It's not like bigger or fatter or um, whatever, right? So those are all equal probabilities. Another form of distribution is what we call the binomial distribution. And once again, this goes back to like a binary two possible outcomes, right? Zero failure, one is success. But as it says here, it's similar to the Bernoulli distribution, but you can't repeat for any number of experiments. So in other words, each experiment that you do is independent of the others. And so every time I roll the dice, it has no effect on the next time I roll the dice, right? The dice didn't like change, right? Every time I do it, it's a separate event, right? And here's the formula for that. What's pretty scary. Does anybody remember what the exclamation point means in an equation? That's the, yeah, there's a factorial. Very good, Jared, right? So if you were like in my, well, if you're in my, have taken my Java 2 class, and a lot of you don't, right? In this program, you won't, but we do exercises about factorials. And factorials are basically where you take a number, for example, if I take the number 3 and put an exclamation point after it, that's like factoring or multiplying that number by all the numbers that precede it. So 1 times 2 times 3 is the factorial of 3. So that's kind of an interesting formula. Once again, the formulas for expected and variance for the random variables. Here's some examples. Find the probability of getting exactly 3 heads when the coin is flipped 5 times, right? This is kind of interesting. So you're, in a sense, each event is separate, but you can conglomerate them with this approach, where the Bernoulli approach is not the same. Or this one's pretty good too. The probability of 3 continuous rainy days out of 1 week. It would rain 3 days in a row. Might rain Monday, Wednesday, and Friday, but we're looking for Monday, Tuesday, Wednesday, or something like that. What's the probability of that happening? All right. Now, this is where I think the author dropped the ball a little bit, and it's probably just to save us like about 50 slides in the slideshow. But there are, if you remember, 3 other distributions that they talk about. Do you guys remember what they were? And of course, the answer is no. But normal, Poisson, and exponential. And what they're really wanting us to do, right? So like if I had a longer class, what I would do is I would take each one of those, assign them, put you guys in groups, assign it to each group, have you research it a little bit and come back with some information about it. But time does not permit us to do that. So I'm going to kind of do a little bit of a sideline here, and I'm going to take us back over to the course shell if I can find my correct browser window. And as I look here, this is, I guess, a little bit of a sideline. I added a couple of references here because when I was looking at W3 Schools the other day, and not only did I find like a whole section on AI that they have now, but now they also have stuff on data science and covering some of the topics that we're covering here in class because they relate, right to the topic. And so, first of all, I'm going to take us over here and just show you really quickly. They have a whole section on data science, and and by the way, a lot of these topics overlap with what we're doing in the AI classes. And you can see just even the names of the things here, right? The correlations and functions and data frames and regression and all that stuff. Um, to kind of take it a little bit further, though, like if you look at the AI section and you look at some of the things and notice how much of AI is really related to machine learning, folks, and the concepts that we're learning in this class. It's really kind of fundamental to all of it. And they talk about plotting and all that kind of stuff. But they also have a little section down here where they talk about statistics, the types, for example, probability is in there. And they talk about distribution. So one of the distributions that he's not doing in the slideshow is a normal distribution. And I feel like this one is really critical to talk about because when you take your stats class, this is like the one they hammer the most. Like if you leave your stats class, this is the distribution you should remember in your head, right? Or not remember in your head, but at least go, okay, yeah, I get it. Yeah, this is important. When we do a normal distribution, and that means our data or the probability of something happening is equally distributed along a bell curve. And there's all these pieces of terminology that go with it that you learn in your stats class, by the way. And they show, for example, here on a scale of standard deviations. And notice it's standard deviations from the mean. So like if we do a probability of, oh gosh, I'm trying to think of like an example of a probability, but let's just say if you take, somebody give me a probability of something to think about here. Maybe horseshoes is a thing, right? Like how many times are you going to throw a horseshoe and get it to hit the pole or to get it within a certain number of feet or whatever? And did you overshoot it, undershoot it, that kind of thing. And what you figure out is that you come up, okay, so Kathleen's saying slot machine reels. Okay, maybe, right? Yeah, I don't think that most of those are programmed to be fair to the user, by the way, right? But basically, whatever the data is, there is a mean for it or an average, and most of the results are going to fall by the mean. And in a normal distribution, the mean is and the probabilities are equally distributed on both sides. And they call this a bell curve, right? And when you calculate these things, 99% of the data will fall within what we call 3 standard deviations. Within 2 standard deviations, we get 95% of the data, but within 1 standard deviation, we get 68 or, a little more than 2/3 of the data. And then it kind of like trails off from there. By the time we get to 4 standard deviations, that's off. Now, all of these are numerically derived values depending on your scenario. And sometimes the data, for example, fits a normal bell curve. It's very structured like this, and sometimes it's not. So sometimes what'll happen is, you will get different sample sizes that you apply to a normal distribution. So the more data that you get, the more accurate and the more defined that curve or that peak becomes. So if you notice, like in this graphic, when they have a really small sample size of 96%, there's a margin of error of 10%, meaning that most of the data that they grab fell in here, but it's such a small sample size, it's not super accurate. So the error margin is huge. It's hard to predict with that. Now, if you do a whole bunch of sample sizes, and you'll notice as you go up the sample size, right, the margin of error decreases. More samples decreases more samples decreases more. And then when you get a really large data set and you know that where the stuff falls most of the time, then you can really kind of narrow down that you can predict with a high degree of certainty that the data will fall into a certain range in that chart, basically, is kind of the point. So this is what a normal distribution looks like when you take your stats class, or if you try to remember back to your stats class, think about, this normal distribution, the standard deviations, how many data points fit inside there. But the general takeaway here, right, is that the larger the sample size, the more accurate your predictions can be, right? If I did a sample size of 96 and the margin of error is 10%, that's pretty big. I could be way off. But what if I only had a sample size of 5? That data could be so bad, I couldn't make any predictions from it. So usually you have to get up to at least some level of data information before you can really take a good sample and really use that information to make a decision or predict, right? That's really kind of the takeaway from it. There's also the margin of error thing, but there's what we call the skewness, which is, does the data skew one direction or another, right? And the positive and negative always go opposite of what you think. Positive skews towards small, negative skews towards large. And then notice what happens to like the median in the middle. It becomes kind of squiggly and weird. And this other concept of kurtosis, which we apply to these rounded curves and stuff, describes the unexpected values in one of the tails. So like you might have a tail that goes way, like you might have a data point like way out here, and they're trying to describe why that happens, and so you can have, the tighter it is, the more certain it is ultimately the thing. They do have a whole section here on probability, right? And they talk about it, and I like their examples, and they have some very nice little examples here. So if you want to check it out, please do so. For a Poisson distribution, and yeah, we'll just go to Wikipedia for that. It shows a different type of distribution, and it really does. And notice like the name here, discrete probability distribution. The probability of a given number of events occurring in a fixed interval of time, right? So for example, how many people are likely to run a red light during rush hour versus how many people are likely to run a red light at 3 a.m.? Well, it might be equivalent. I don't really know, right? Because the 3 a.m. person might be coming home from the bar, and not seeing the light at all, right? But the whole point is it has that discrete aspect to it. It also has a time interval, which becomes important. So that's a Poisson distribution. And I'm trying to remember what the last one was, and I don't. So let's just flip back to the PowerPoint now and carry forward. I am going to exponential distribution. Let's just Google that one really quick, and then I think we're about ready to take a break. All right. So once again, I'm going to go to Wikipedia on this. So notice the definition here. So they also call it negative exponential distribution. It's a probability distribution of the distance between events in a Poisson point process, in which events occur continuously and independently at a constant average rate. Okay, so this gets pretty technical, but you can see like how there might be application to stuff like this in like a car that is undergoing machine learning to not hit people or other cars, that type of thing, because there's a time aspect and you're looking at analyzing or the negative distribution of the time aspect. All right, let's go ahead and take a break. When we come back, we will move on to the next slide, but we're going to do 5 minutes. So it's 8:51. We'll be back at 8:56, and I will mute myself, and I'll see you guys in 5. All right, folks, we're back from break. And while, normally in a regular super long class session, I would have you guys like attend to this as an exercise. And I did consider making it an extra credit exercise as well, by the way. but I thought it was better just to provide the information. I basically took the information on this slide and posed the following question to Chat GPT. So this is my prompt, right? I just took questions straight off the slide, and then it generated this content, and I took that content and I added it here in our class shell. So if you click through to this, and of course I have to like refresh. There we go. All right. Talks about each one of the distributions. It talks about, the density function, right? And etc. Talks about each one of those. And it also has an example of how they might be used. So they're saying here, okay, so I don't know why I don't think about this stuff, right? They're talking about like the average height for humans is about 170 centimeters with a standard deviation of 10 centimeters. And so you can model and predict the probability of somebody being within a certain height range, right? Or with the Poisson distribution, modeling the number of incoming calls per hour. Notice the timepiece on that, right? On average, 10 calls arrive per hour. So how many calls would you expect? Right? That kind of thing. And then exponential distribution, the time between arrivals of buses at a stop, assuming the buses come randomly, but on average every 15 minutes. This is like really weird stuff, but you could see, like, if I was a person who was scheduling a bus line, how that would be very pertinent, right? Very, very pertinent, because yeah, the bus is supposed to be here in 15 minutes, but there's traffic and there's lights and there can be accidents. And, these days protesters too, get in the way of traffic, and I'm just making light of things. So I hope you guys are not offended by that. All right, let's go ahead and now look at another really important theorem and classifier. Bayes' theorem is a really important statistical concept and very applicable, by the way, to machine learning. And so right away we go back to, I should say, the concept of the conditional probability, right? The probability of A happening if B has already happened, right? So what if we want to flip that, though? That's the second bullet. What if we want to flip it and go the other way? What if we want to know the probability of B happening if A has already happened? So is there a way to find that? And Bayes' theorem was basically created to figure that out. So they go through an entire mathematical proof here to understand why, it works and what it means, right? And I do not intend to ever really formally super heavily quiz you on this or anything like that, or memorize this. But if you were in a stats class, you probably would, right? And good luck to you, basically, right? Because I remember what a nightmare it was to initially learn. But if you want to do the proof on it, there it is. So we end up basically with the formula that you see on the screen here. And I know that looks complicated, but just remember, this one stands for the probability of B happening. This one stands for the probability of A happening. This is the conditional probability. And these are all calculatable. It's just that when you put them together and try to do proofs, they look complicated as heck when you put them like in a formula and go through them step by step. All right. That aside, let's take a look at the second scenario, the one that we're using it for, which is trying to figure out if B will happen if A has already happened. And they're saying that this probability is posterior, and this is the one conditional probability that we want, right? Or we want to know about. And we already know the other one, which is what is the likelihood of A happening if B already happening? And we already know this, right? Because we calculated it for whatever reason. So the probability of B happening alone is knowledge that we know, because if this is the one we know, this is due to the fact that B has already happened. So we know what its probability is. And then the probability of A happening is what we call the normalization constant. And this is the marginal probability, right? We've talked about that singular, right? That's the marginal. Um, in machine learning, by the way, the A's and the B's usually have meanings. The B's usually refer to the labels, and the A refers to the features. And if you think back, right, we talked about features and dimensions of data, right? Where all those, like, those extended feature sets or dimensions are, where some of the real information is. And those are also usually where the unknowns are as well. Right. So they have an example here of how to use this, right? And I know they have it in formula, right? But basically, the scenario is this: we know the probability that the patient drinks alcohol, right? And given that he has liver cancer, can we find the probability that the patient has liver cancer given that he drinks alcohol? Okay, so in other words, somebody has liver cancer, right? And we've linked it to the fact that he drank a lot of alcohol, right? But what's the likelihood in the converse? So, like, just because you drink doesn't mean you're going to come up with liver cancer. You understand what the scenario is? So, the A here is drinking alcohol. That's the features. And B is liver cancer, which we're labeling. Okay. And, so what's the probability, and look at how this is written, of liver cancer happening if you drink alcohol, right? So the alcohol is a given that it is happening. Or how about this scenario? We know the probability of it raining given that our friends play tennis. Can we find the probability of her playing tennis given that it rains? All right. Once again, I want you to, like, just ponder this for a moment in the back of your head and let it sink in a little bit. So in this case, A is the rain. Those are the features. Is it going to rain or not? And playing tennis is the label. All right. So what's the likelihood that this person is going to play tennis if it's raining? Well, I live by some tennis courts. I see people playing in the rain, believe it or not, quite often. Um, it's just a thing. So some people do it. All right. So what they're asking you to do here, and this is another one of those things I would like to do an exercise if we had a longer session, to write the Bayes theorem for the following scenarios. So if you want to find the probability of a autonomous car stopping given it sees a pedestrian walking, or you want to find the probability of the patient being COVID positive given he is coughing. And by the way, COVID's been going around again. And I don't know if I mentioned that last week. So people are still getting it. Or if you want to find the probability of credit card fraud, given that the amount of the transaction is over $100, right? Because if you're going to defraud a credit card, you're not going to do it for $5, right? You're going to do it for big money, right? So what they're telling us now is that, okay, we're looking at situations that have single features or single dimensions to examine. What happens when we have multiple features or data points or dimensions to deal with? And that's where the naive Bayes classifier comes in. So you have the original formula here. And then if you have more than one feature, then all of a sudden you have multiple A's. It can give you one or two or three, all the way up to whatever unknown number we don't know. You can take that in the spots where all the A's are in that original equation and subtract them with this series of unknown values, right? And how many values are determined by your situation, right? So if you have 5 data points or 3 data points or whatever, that's how many A's you have. But they can all be added into the equation. So here's an example of this. You're planning to watch a movie with a friend. They don't tell you what they like in a movie, but every time you try to pick something, they say yes or no, right? So you investigate a little deeper. I don't know if they're doing Q&A, and think of some of the contributing factors. So maybe they want to see a blockbuster, or maybe they like romance movies, or maybe they just love Tom Cruise, um, or maybe her sister watched it, so she wants to watch it so they can talk about it. That kind of thing, right? And I don't know, and all of us have criteria like that. I'm like, oh, I like that actor. I don't like that kind of movie. You know, my friend saw it, so I want to see it. So those are all pretty reasonable. And so what they would do is they would take all of those data points, right? And those become the A's in the equation. So what's the probability of watching the movie given that it's a blockbuster, a romance movie, has Tom in it, and her sister watched it, right? So now we're looking at 4 data points. And man, if you can strike all 4 of those, you're going to watch it, right? And maybe if you strike 2 of those, you might watch it, but maybe if you only hit 1, you might not, right? So you can see kind of the example and how that kind of builds. Now, why this is useful, right? It is a very quick way to predict things with a data set, and it performs really, really well compared to other models. Um, but there's that assumption that you see at the end there, the features being independent of one another, right? So a movie could have Tom Cruise and not be a blockbuster, and their sister could have watched it and it might not have had Tom Cruise. You see what I mean? Like, all of those things don't all have to check the box, right? So all the features are completely independent, right? Now we're going to look at another classification system for making decisions with machine learning. And there is this thing called a decision tree. And we're going to learn what it is and how to make one. And there are methodologies for this. And to not to complicate things, but there's more than one type of decision tree, and there's different algorithms for building them, and you can do it in a lot of different ways, by the way. All right, so here they're calling a decision tree a type of supervised machine learning technique. It iteratively splits according to conditions. So it as you cycle through the data, basically, it adjusts to it. You can split into a bunch of different branches, and each time you split, you're basically making a choice on a certain condition, right? So like you're driving down the road and you can go left or right, right? So you go left, then you drive down the road, and then you can go left or right, and then you go right, right? But you get to a split and you basically have a choice. Now, the concept is when you have multiple conditions that are driving it, that you have a logical pattern that you can follow that's systematic and hierarchical, that you can make the decision of whether something is happening really clearly and simply. Now, there's a bunch of terminology that goes with working with trees, and part of it I'm going to like annotate here a little bit. So you have the root node, right? It's the very first node at the top. It has no node above it, and it may have 0 or a few nodes at the bottom, but usually it'll have something below it. So the root node is the top node. Then we have an internal node, which is one that is inside the tree, but it hasn't reached what we call the leaf, or the end of the line, so we know what the decision is. So like, for example, in this chart here, this is the root node. These are the internal nodes, the ones that don't directly lead to one of the leaf nodes. Right? An internal node will always have one node above it and definitely have a node below it. Right? A leaf node is assigned a class label, and it can either be a pure or a majority vote, right? And so basically, it's kind of like, for example, rain or not rain, would be an example. Cloudy, not cloudy, that type of thing. And then we have this other terminology with the parent-child thing, and we say when a node is split, this is the parent node, these are the child nodes, right? These are pretty common, like coding terminology conventions too, by the way. what's really fascinating about a decision tree, such as the one that we're seeing on the screen here, is this is a way to structure information in and of itself, right? And if you do a deep dive into learning how to program, usually when you do a couple levels of a programming language, you get to like level 3 and 4, then you start getting into data structures, and a decision tree kind of falls into that type of data structure area, by the way. All right. There's a few different types of decision tree algorithms. There's not just one, not to make things complicated, but it is how it is. Um, in this course, at least for now, we only look at the binary decision tree. Output is binary, meaning that every node splits into two branches, right? And we typically call this a binary tree in the data world. And usually we think of it from the Boolean standpoint. And Boolean is a coding way to say true or false or yes or no or one or the other, right? So therefore, it says for n features, there can be a maximum of 2 to the m potential split. So for every node, that can split to two different things. No more, no less. Okay, that's the general approach to it. So what's the benefit of doing this? Okay, it says all possible outcomes are displayed in the tree. So every possible thing that could happen is shown. And then it allows us to really analyze things deeply, because if all the possibilities are on the screen, it's just a matter of which branch we're following or node or whatever to get to the leaf, right? Easy to use because you look at one decision at a time, right? As you traverse the tree, it's kind of like you reach a node and then ask a question and it splits. And every time you traverse it, another thing, one decision at a time, right? Not all of them at once. It's very easy to understand how you get to the outcome from the decision made. And really there's other benefits too, but those are kind of the key ones. All right. So let's look at this scenario. It says you're deciding if you want to go to the park for a picnic later. The possible factors include, will it rain later? Do you have picnic food ready? Is your friend joining you? And is it crowded? And so your decision tree might look like this. And this is not a formalized one, right? And so basically what we did is we took all the questions here and we put them in the slide and we just said yes or no, right? So first we asked, is it going to rain? Okay, yes. What's the outcome? And really there should be a line here, right? The outcome is stay home, right? Okay, it's not raining. Then the next question, do you have picnic food? Nope. Well, then I'm going to have a sandwich at home before I go, right? All right. Right. Well, if you're trying to do a picnic, I guess you're going to eat. So I guess you're staying home if you don't have picnic food. If you do have picnic food, I don't know, sandwiches, chips, whatever, a bottle of wine. So you do have the food, so you're going, and then you ask the question, is your friend joining? Well, no. Well, all right. Well, I'm not going to the park then. I'm just going to go to McDonald's. If my friend is joining and I have picnic food and it's not raining, right? I'll meet my friend at the park. But you notice how I didn't have to ask each one of those questions all at once, right? I asked them one at a time and then made a decision. So depending on what is happening, you can make a choice, and the decision tree helps you to get there. That's the grand takeaway. All right. Now, how about this scenario, right? And I know we go through these questions once in a while, like deciding if you're going to buy a new phone, right? And I've come to the conclusion lately in my life that, you know what, I really don't need the latest greatest phone anymore. This one works just fine. It keeps working and it's paid off, so I don't have to make payments on it, et cetera, right? So what are the factors that influence your decision? Well, is it better? Is it a better phone? That might be one, right? Like, do you my phone, how about this? My phone is broken, so I need one anyhow, right? But do you want one that's fast? Do you want one that has a good camera? Do you want one do you want an iPhone or Android? Do you, et cetera, et cetera. How much does it cost? How much data do I get with it? What other, for some of you, does it have a headphone jack? right? Because all the new ones are like Bluetooth now, right? They don't, you can't even plug your old headphones into them, all those types of things. And then if you were to make your own decision tree, right? And once again, if we had a 4 hour session, I would maybe have you do this. Like what factors would you make? And then how would you decide which one to get? Like another question might be like, do you want to switch carriers? Do you want to switch to a different company at this point? Maybe, maybe not. I don't know. Right. So these are things that you would ask. Right, let me clear that little annotation there. Right. All right. So then if we were to make our own decision tree, and we could follow the RAIN one and you can make it like whatever logic works in your brain, right? And I think about like my programming classes, so like Python people, right? It's like, hey, if I have $20, I can order a pizza. If I don't, I'm staying home, right? And I'm making mac and cheese, right? You remember all those like scenarios. But is there a system for doing it that can determine it? Okay, so here's the scenario. If we want to play tennis tomorrow, um, okay, you want to play tennis with your friend. Sometimes he plays with, and other days he doesn't. You want to know what factors may affect his decisions. Thus, you diligently take notes of his decisions with respect to the weather. So you keep a little notebook on your friend on when he shows up or not. That's kind of weird, but people are like that, whatever. All right. So you have a thought. Can I build a decision tree to predict his decision if he will play tennis tomorrow or not? Okay. So let's kind of follow through this. Now, if you look at the dependency files for this week, this data file called tennis, right? And there's a couple different versions of it, has a table of information. It indicates the day. So like for a couple weeks worth of days, the forecast is the outlook, right? The temperature, the humidity, the wind, and whether or not tennis was played that day. So he like made this little chart. Like it was sunny, it was hot, it was humid, and there was no wind, and he didn't want to play. Right. And so he just kept records of all this. And this can help you build a decision tree because um, the data helps to drive it. Okay. So we can look here and say all the reds are yeses, all the black ones here are no's. So there are certain scenarios where he says no, and you got to figure out what those scenarios are. And it's not just because it's raining. You guys noticing that? Right? Because I do see a rain day that's a yes. In fact, I see a couple of rain days that are yeses and several rain days that are yeses. Right? So, all right. There's a few different algorithms for doing this, by the way. These are probably the top 4 that people use. And we don't have time to go through all of them, obviously, right? So we only have so much time in a day. But we're going to use the CART algorithm because it is commonly used to do classification problems. And more importantly, it has a Python library that we can use later to help do the work, right? So that we don't have to create the code from scratch. So you can read about those other ones separately, but if you deep dive into this decision tree stuff, these become a thing to study. There is some math behind it. Once again, I don't want to freak you out with the math, but basically what we're looking here is the weighted sum of the Gini index. And we have this thing called a Gini index because this is what drives the math behind this, right? And so we have this formula, we pump a bunch of values into it, and then what we do is we pick the attribute, or basically the data point that has the lowest Gini index value, and then basically use that as our root node, and then we build the rest of the decision tree from that. So there's a mathematical way to decide what question you should ask first. So this is kind of interesting. So that Gini index, we also call that the Gini coefficient. It measures the distribution of how much they vary between one another. A higher index number indicates large inequalities. And if all the data points point to the same outcome, the index is 0. So it goes basically, bigger the number, the larger the inequalities. It says in machine learning, the purpose is to measure which class would give the least variance. So for example, all the predicted output should be of the same label given the conditions of the features. All right. So they go through the process of showing you how to figure that out. So like you can do this by hand, right? And before we had computers, people would calculate this kind of stuff by hand, unfortunately, right? So, all right, they start by looking at um, the index for the outlook column, which is the forecast for the day, right? So they look for first the keyword sunny. There's 5 occurrences for sunny. From these 5 occurrences, 2 are yes and 3 are no. Okay. So now we're tabulating it. So now we're saying the outlook for sunny is 2 yes, 3 no for a total of 5. Okay. All right. Now they look at the overcast prediction. So there's 4 occurrences of overcast, right? And out of those 4 are yes and 0 is no. So apparently they like to play on a cloudy day. That's intuitive, right? Right. So we put that in the table too. Then we look for rain. Once again, 5 occurrences for rain, 3 are yes and 2 are no. Now I would think on that one they would be all no, right? I don't know play in the rain, but if you ever play tennis, you do get pretty hot when you play tennis. So maybe the rain feels good. I don't know, right? Or maybe they win more when it's raining. I'm not really sure. Okay, my dog just paid me a visit here. I was like, just strolled in, made some noise, strolled out. All right, that's in the video now. All right, so what they did is they took that formula, by the way, pumped in all those numbers, and came up with a result, right? So what's the Gini index number for sunny, overcast, and rain? And this is on one feature set, mind you, right? And they came up with these values, and you notice 0.48, 0, and 0.48. Right. So overcast was play every time. Okay. All right. All right. Then they calculate what they call the weighted sum for outlook, and they take the number of instances, right? Those are the underlying numbers, and they take the number that of the occurrence, the total occurrences, and the Gini index. They do the math on it, and they come up with a number. So the Gini index for outlook ultimately is 0.34, like if you calculate it out. And then you can do the same thing for temperature, right? So I'm gonna rifle through these a little bit faster now, right? So we can kind of get through them all because we're running out of time quick. So for temperature, they look at hot, mild, and cool, right? Here's all the results for all of that, right? They do all the math on it, and they come up with a 0.441. Then they move on and calculate the others, right? So you notice normally in a longer class session, I would try to make you calculate these. Like you guys are like, thank God we don't have to do that, right? And then they come up basically, so they compare outlook, temperature, humidity, and wind. And then we look which one has the lowest Gini number. And that answer is outlook. So the forecast is the root node, right? Not because we think it should be, but because the math tells us it is. Right. So this is really the fundamental difference of it rather than intuition. Although that seems like, hey, it's going to be beautiful today. Let's go play tennis. That makes a whole lot of sense, right? It really does. So if outlook is the root node, then we branch from there to 3 different possibilities, which is sunny, overcast, or rain. All right. Then we identify all the occurrences of those, right? So outlook is the root node. These become the internal nodes. Parent, root node, subnode, parent node, child node. And then we can kind of break it down from there. And so as we kind of go through these, you'll notice that we look at temperature, and then we look at temperature's 3 conditions: hot, mild, cold; humidity's conditions: high or normal; wind, strong or light. right? And then, yes, you can calculate all of those as well. And then you get Gini numbers for each one of the subcategories, right? And as you start to kind of like plow through this and you start looking at humidity, well, when the humidity is high, they certainly don't want to play. That's probably it seems like one of the biggest drivers, although when it's raining, whatever. All right. Um, and then we can look also at the humidity factor here and the wind strength, right? Notice the numbers that are being generated, right? And so they, once again, calculate and they say which one has the lowest Gini, and then we'll choose that as the node. So what they're doing is humidity had the lowest number. So under sunny, we then ask about humidity, right? It's sunny out. Is it humid? Yeah, it's 95 and humid. I'm staying home in the AC, right? Or, it's 85, but it's normal. It's like 40% humidity. I can deal with that, right? All right. So that does that. Now, what they do ultimately is if you follow through with the mathematics on this, right? And you can see that it could be a tedious process because you have to have the data, you have to look at the data, do math with the data, process all that information, decide what nodes are what, and then you end up building. And the decision tree that they come up with is basically this, right? This is the final output of the decision tree as a graphic. So first we look at the outlook: sunny, overcast, or rain. There's three possibilities here. So this kind of a little bit breaks the rule, but it still forms each one of these. And normally we'd want to see a branch, but this is branching to a branch that then comes out to leaves. But ultimately, if it is sunny and high humidity, it's a no. Sunny and normal, it's fine. If it's overcast, that's fine, right? Because it's not sunny and it's not raining, it's overcast. And then if it's raining, if there's a strong wind, no. But if it's a weak wind, maybe yes, right? Not maybe yes, but definitely yes. Yeah, and I'm looking at what Finley had just dropped in there. Yeah, and you know what? Sometimes decision trees um, are enforced. And you know what? You're in the support world, Finley, right? And sometimes, um, in call centers and stuff, they have trees like this. It's like, have you tried rebooting your router? Yes or no? Right? Okay, that didn't work. Has a squirrel chew through the power line? Or yes, that kind of thing. All right, so now we're reaching the point where we can see how we can apply all this using Python. And what the author did here, which is a little bit unusual for him, is they put all the code snippets, the same ones that were in the dependency files. And I'm trying to see if I have dependencies sort of relatively here, right? So this is kind of the same information that's in this HTML and notebook file here with the decision tree. So you have the notebook where you can borrow the code from, and you have an HTML version of this too, which really kind of talks about the process of doing it. The tennis files with the data that we were just looking at, and an Excel version of the same thing. And then the library that you might be missing for Python. Although what I will just very quickly say is that as you look at the code that you need, you will notice that there is this new library that we haven't used yet. So you'll have to do an install either in Anaconda or via a pip command. Earlier tonight, I did a pip command on this machine, and I just typed pip install graph viz, and it worked, and it was really quick. I didn't have to download anything. Now, what the author here did is, I don't know if maybe at the time he put this together, he wasn't sure that this was an easy plugin to find. He included the installer here. I would not recommend running the installer. It's there if you want as a fail-safe, but I think doing a pip command or using Anaconda to install it is probably better, right? And the pip command literally took like 2 seconds, and it worked, right? You just go to your command prompt, you type in this, pip install graphviz, downloaded, installed, all done. Thank you. You know, on with my day. Right, so I'm just that's the precursor. All right, back to the PowerPoint. All right. All right. So they talk about the libraries that we're using. Pandas is being used, NumPy is being used, Plotly is being used, sklearn or scikit-learn is being used, and graphviz is being used. We're also reading in the tennis file. Now, you can use this code right in these sample files, by the way, to do your homework. And I would encourage you to do that step. All right. They do talk a little bit about difficulties in installing this. I didn't encounter any, and I'm anticipating it'll be the same for you. So maybe this has become a more standard library now and is easier to get. If you run into problems, I would prefer that you reach out to me first rather than try to fix it on your own. I would anticipate none of you will really have a problem. But if you do, let me know about it so I'm aware. And if you figure out a solution, great, let me know that too. We will run the pandas command to read it in a CSV file. This is something we've done before. So we're going to take that tennis data, same tennis data that we were looking at, and read it in. Right. 14 days worth of data. And it says, how many entries are there? Does the data come with a header? How many features are there? Well, I'll tell you what, the only way you really know that stuff, and once again, open up your data files and look at them. You know, this is like really rudimentary kind of stuff. How many data points do we have? I don't know. Well, look, you know, and so here's my CSV file opened inside of Excel, and you see the data set, right? So yeah, there's a header row. Okay, why is that important? Because when pandas reads in the file, it needs to know that that's a header row, right? That contains information about the information. If you happen to look at the Excel file, right, and I'm going to open that one too, you'll notice this is basically the same thing, but you notice it has like Excel filters on it and things like that. So if you wanted to, for example, filter by, editing's not turned on, but you could filter your information as well. Either way, I would prefer you use the CSV file to do the data. I noticed there was a second tennis file also. And if you notice, this one just has more data points. So that might be an interesting one to work with. All right, moving on. All right, so, okay, actually, let's go back to that question because we didn't answer the question. How many features are there? How many features are there, do you think? Some of you might say 4, right? Why is this one not a feature? This is the outcome we're trying to achieve, right? These are the data points that drive that outcome. Is the number of the day important? Probably not. Technically, okay, so if this was a date, maybe that would be important because what if it fell on a holiday? That would be relevant, right? Or it fell on a work day. You can't do it on a work day, whatever. But generally, this is a dimension that we can probably ignore. But I would say 4. All right. So we start by doing label encoding. So like you'll notice that they are labeling the outlook, temperature, humidity, and wind. Notice the code that they're using here to do that, right? And then they also have a little information here. It says the decision tree classifier only accepts numeric labels. Hence, we need to change the format. There's 2 options. We can use label encoding or one-hot encoding. In this example, we use label encoding. So what they'll do is if it's sunny, we'll use the number 2, right? If it's overcast, 0. If it's rain, 1. And then temperature 1, 2, or 0, etc. So they've put numeric values on the states. Now, those states are independent of each other, but the why is because it's easier to act upon the numbers than it is to act upon the labels. We then go into splitting our data, right? And so we set up a data frame where we're pulling in these features, right? We also have the play tennis, we're data frame with the values, and then we're going to train. So in other words, we're going to split the data. We've talked about this in the previous class, right? When we do training of a model, we don't want to use all the data to train the model because then we have no data to test it with. So the test size is 20%. So the training size is 80%. So that's pretty normal. And this is a number you can alter and play with, right? And there's different schools of thought on how much training you need to do and how much testing you need to do. Somewhere between like 60 to 80% is usually the training data, by the way. All right. Then we go to this code here, which does the modeling. So in other words, we are telling it to use the decision tree classifier, and we're pumping into it the training data, right? Then we start to run the prediction tool, right? And then we predict off of the training data and we predict off of the test data. And then we can do a thing where we can compare. But ultimately, what it'll do is it will create in a print form, basically the number of classes, how deep the tree is, the number of leaves, and the number of features, right? And this will just output this information, right? How much tree, how deep it is, how many leaves, how many features, right? And that just comes as text on the screen. Then we can kind of look at the accuracy score. So we look at the training data and basically see how accurate, what kind of precision were we getting basically doing that. And it says the accuracy score is 1. Okay, that's kind of a weird number. But it seems like it's a good number. What do you think? Well, we don't know. We don't have any criteria by which to judge it. But what we look for is, these scores and how they're supported ultimately. 1 is really good, by the way. So you may not get an accuracy score of 1, meaning that your training worked out really well. But that's kind of what you're shooting for. So, and they ask the question here, like, what factor would really drive basically or influence the accuracy of that score? Well, here's one example. The data that you captured is wrong. Or if you were converting from sunny to the number 2 or whatever number it was, you didn't do that correctly. Or there was a different scenario that was added as a data point that didn't fit any of the other data. Those are some scenarios that would do that. There is the ability to also generate a graphical tree. That's what the graph viz is all about, by the way. And they're showing this as a potential output of the decision tree. So they show you here, right? That the outlook is the root node, right? They give you the Gini number, the number of samples, the values, etc. And then they kind of break it down. And if you notice, it follows, maybe a different format than what we came up with in our approach. The whole point is all of it is represented here, so you can follow through this tree and still make the same decision based on a future data set. So if I'm given a random set of those 4 features and plug it into this model and then just answer the questions, yes or no, it will tell me if I'm playing or not. That's the point of it, right? And this, notice that this says this is a potential output of the decision trees, right? Not that it will be exactly this. And it says it will vary due to randomness applied to the split data. So in other words, where you put the split point in, if you decide to train with 70% of the data or 80% of the data, will change how this is generated and might even change the structure of it. Right. So that's one thing that people mess with is the amount of training material that they throw at a model versus the amount of um, data. Once again, the tree depth, it's 3 layers deep. Root node goes down to 1, goes down another, and then ends up at a leaf. So 3 layers deep. Right? The number of leaves or the final decision points, these are all the endpoints, possible paths that you might end up on. Right. And as you start to break this down, and it says outlook less than or equal to 1.5 refers to the outlook 0 overcast and outlook 1 rain. And that's what they're trying to tell you there by combining those two. Ginny refers to the impurity. It means that there's only one label, right? And there's a value of yes or no. And class is determined by a majority of the label. Now, in this case, what's the outlook? And I want you to think about this. They're doing a true and a false on this, but if you remember the outlook, I think there was maybe 3 situations, right? Do you guys recall that or not? It's like overcast, sunny, or rain, I think were the things, right? Right. Right. So when you play with this, it says try to rerun this a few times and then notice what happens when you do it. Now, we're at the point where we're kind of out of time, so I'm not going to be running the code, by the way. I'm going to leave this to you. What I may do, and this will probably be a couple of days out before I do it, is I might run the example and record it and then publish that separately as a video so you guys can see it. And then that'll help you at least feel more comfortable maybe in creating your homework. Then the question is, how do you improve the accuracy? All right. And then modify the parameters in the decision classifiers and what are the impacts, right? And you can imagine the whole point of this, right? And if you're not feeling it, is get this to run, see what it does, tinker with a few of the settings, the ones that we talked about, and see what happens. What are the impacts? How does it change things? Does it change the accuracy score? Because ultimately we want a good accuracy score. All right, just about out of time here, but what I'm going to try to do is hit these last few slides here as quickly as I can, right? Real frankly, we don't have time to go deep on this. And if you need to leave at 9:50, I totally get it. I'm probably going to run a few minutes over, but I do want to finish all the slides. So I welcome you to stay. Otherwise, you are free to go. All right. So it says here, we're going to look at different applications of machine learning models that use decision tree algorithms. For each of the applications, we'll discuss what are the features we can use to build, how easy or difficult it is to collect data, and what are some ethical considerations regarding features selected and approach taken. Okay. And I see a typo there I should fix next time. All right. What if you were categorizing a customer bank loan application? What are the features that we can use to build a decision tree? Okay, so let's talk about this, right? Because I think this is a pretty obvious one. So somebody's filling out a loan for an application. What types of information do you look for? I know some of you have, salary, yeah, big time, right? How much money do you make? All right. Can we see your last couple of bank statements? Okay, well, that's your salary, but what's your rent? Right? Like they also want to know what bills you have, right? Like, can you afford to make the payment? That kind of thing. How easy or difficult is to collect data? Yeah, debt, right? So if you have to pay bills, absolutely. And most of the time on a bank loan application, they're usually assuming that the person's telling the truth, but they might ask for your tax returns, or why do they want to look at your bank statements? Because they can see how much money comes in and how much money goes out. And not only that, see what you're spending it on. Oh my God, They're ordering DoorDash every night, you know, or whatever, no judgment. All right. Next scenario, prioritizing patients for emergency room treatment. All right. Okay. So I can tell you one that gets you right in there right away. Bleeding a lot. It was like straight into the procedure room. Right. How do I know this? Because it happened to me once when I was younger. I cut my hand really bad on a piece of glass and it would not stop bleeding. And I came into the emergency room with a blood soaked towel and it was dripping everywhere. And they're like, come with us. you know, um, Meanwhile, I've gone in with a broken bone and it hurts and it's disfigured and it's like, have a seat. We'll call you. Right. So they certainly have scenarios, right? Like if your life's at risk, losing a lot of blood puts your life at risk. Breaking a bone is like, ouch, that hurts, but you can wait a few minutes, right? Here's some aspirin, you know. So um, so what features can you use to build a decision tree? All sorts of things. Another one, right, is do you have insurance? Right. We don't want to say that one, but that is one, right? Oh, like for example, I live on the east side of Milwaukee and near a big hospital and we have homeless people in our area, right? It's a densely urban populated area. And if you end up in the ER on a weekend, typically, there are a lot of people in there just trying to just come in to warm up in the winter, or maybe they can get a free meal out of it, or whatever the deal is, right? And sometimes they deprioritize those people, and unfortunately, right? And it's just the nature of society. So um how difficult is to collect data? Well, if a person's like dying, you can't really ask them any questions, you know, uh, but maybe you can. Who knows? Another application: shortlisting a student for admission or scholarship. Hmm. Yeah. By the way, Gateway is not one of those institutions that really kind of does this, right? We have a very open policy here. We want everybody to come to school here, right? Because we know technical colleges are the best, right? And I say that jokingly because I've taught at many different levels, and I kind of really do sincerely feel that. I think that technical education gives you more bang for the buck, more value, and can really open the doorway to other levels of education at a much less expensive price. But what is a factor that a school might consider for admitting you? Now, Gateway doesn't really do this, but I know that there are a lot of schools that won't let you in, like if your high school GPA wasn't X. Yeah. And therefore, I was denied a lot of universities, real frankly, because I had a horrible GPA in high school. Horrible, you know? Um, but when I got to be a serious student, that changed, right? What other factors, right? Your GPA. Um, how about like if you're going for a scholarship, your need? Like they might look at your family's financials and go, "Oh, you guys are rich. You don't need a scholarship. You should pay, right? This person doesn't have any money. They're perfect for a scholarship." Or maybe a scholarship is based on merit. So maybe they would look for certain English or math scores to give you the scholarship. So, once again, it's all driven by data, right? Unfortunately. Um, and this is a really interesting question. Yeah. And Jared, yes, correct. All right. There's a lot of different examples that we can apply this to, by the way. And does it bring up any potential ethics problems? Absolutely, it does. Right? If you have decision trees that affect people's livelihoods, finances, education, et cetera, et cetera, et cetera, et cetera. Yeah, you really have to think about this stuff and what those problems might be. So if you're denying people of like who aren't smart enough to get into a college entry, well, of course, all your students are going to be great, right? I mean, and traditionally, I want you to think about this. This is exactly what universities have done to us, right? Hey, if you want to go to Marquette, you better have really good grades or a whole lot of money and know somebody, right? and a recommendation. And that's how it's kind of always been. But that's starting to change now. It is, right? Schools are aware that it's not good. And that just because somebody doesn't have great grades and doesn't have money doesn't mean that they can't be great, you know? Um, and I'll be a perfect case example of like somebody who was not a good student in high school, not a good student at college when I first started either. And I figured out a way to turn it around and make it a career, you know? So, I mean, it is doable, you know? Yeah. And Kathleen, yeah, insurance coverage, uh, life insurance, et cetera. Yeah, absolutely. Right. And that one's really data driven. Here's one thing I complain about often with like insurance is like our car insurance here east side of Milwaukee. The amount I pay for car insurance monthly for all of our cars for the whole family is about what most people pay every 6 months if they live in the suburbs. Why? Because of the zip code I live in. Right. And unfortunately, 3 nights ago, we had somebody smash windows on like 6 cars on our street and do smash and grabs. And my insurance rates are not going down. you know, um, my only combat to that is to own an old car and make it one that nobody wants to steal anything from. And in fact, don't even lock the door. You know, go ahead, take whatever you want. Right. Yeah, that's that's the unfortunate reality. All right, folks, that really wraps the lecture here for tonight. From here I go for quiz and assignment. I do plan on hopefully recording a video, stepping through running the code as a sample. I might even do that tomorrow morning because it shouldn't be too time consuming. When you work on the homework for this one, make sure that you look at the example code that's provided in the notebook, right? And just follow these examples and then ramp up the data to meet the scenario in the assignment. The assignment itself, and I'm just going to kind of bring it up on the screen here real quickly, has you ask which features do you use, how many data sets, how many rows of data, and what Python code, right? And it kind of guides you, right? The scenario is that you have a Fitbit kind of device and you want to monitor the data on it, and you want to create a decision tree. So if you want, you could generate false data if you wish, or if you want to try to apply this, you can also augment it with the tennis data that we already have. If I can generate a data set for you guys to use to augment this, I will attach it to the assignment. That wouldn't happen until tomorrow at the soonest, though. All right, folks, that wraps the session for tonight. Thank you all. And this video ends here.